Okay, so we have two more talks in this session. First by Benny Kimelfeld on measuring the importance of database elements.
Okay, good. Thank you. So yeah, you can see the slides okay? You can hear me well? All right. So first, thank you for having us online. And I've been watching the workshop live during the week, every day. It's a great workshop, great talks. And I could also recognize the voices of great people. So it's a pity that we cannot be there due to the circumstances. And I'll do my best to convey the story. And so I'll talk about the importance of database elements. And I'll start with the importance of database tuples, but I didn't synchronize with Daniel. He essentially said everything that I wanted to say. So, we can go directly to the questions. But yeah, I'll put the stress on some other aspects. But so this is work with great colleagues, especially Esther Lipschitz was behind most of the work, and Leo and Michael and Daniel and Nabil Frost. So importance of database tuples. So here's a toy example. So you have a query saying that there exists a case where a person who is paid low manages a person who is paid high, okay? And then contrast to, say, the intuition, and then we look at the database, or the low paid, the high paid, and the database says, yes, there are cases where this happens. And we say, why is it the case? We want an explanation of why it happens. And the situation is that we have a limited attention budget. We do not want to get all of the homomorphisms, all of the answers, all of the assignments of the variables, but rather a concise explanation. And we want this explanation to stress the parts that are more impactful. You can give me like an arbitrary homomorphism, but I would like to be able to measure, quantify the importance of the tuples according to their impact on this query, their responsibility for actually making this query happening. So you can see here, for example, that there's a person who is managed by several people who are low paid, and that explains many of the occurrences. So this person is probably overpaid, or a person with a low salary who manages many people with a high salary. So this person might be underpaid. Okay, so if we stress these or we use these tuples for an explanation, we get a much bigger or a bigger part of the story. Okay, so this is coming from the descriptive viewpoint. We can also look at it from the prescriptive viewpoint. Okay, suppose that this is an issue, like this is something that shouldn't happen maybe in reality, or maybe this shows some problems with the data. So we would like to fix it, repair it. And now we have a limited repair budget. So then we would like to start working, or to put our partial effort or effort in partially fixing the database on the hotspots, on the tuples that will maximize the benefit of our time, even if we're not going to fix it fully. Okay, so this is a example. In this case, this responsibility quantity, just counting degrees. It can be more complicated if you have something like, X manages Y and Y manages Z, and then X and Z are family members. Then the contribution of a tuple can be more complicated. Okay, more serious use case is, for example, in this work of Dosso, Davidson, and Silvano, where they looked at the problem of data credit distribution. Okay, and they they wanted to quantify the credit or to credit data sets according to their contribution to scientific publications, okay, data sets and data curators, okay, so they have a database of publications and references between publications and the data sets, and the interesting thing is that, you know, they use the generic explanations or say contribution quantities from the database, because they just had a relational database, and in this relational database, every publication is a tuple. You see every rectangle here is one tuple, and every data curator is a tuple. So they use generic quantities for the contribution. By the way, I use contribution, responsibility, importance. I'll use them as synonyms. Okay, and you can see that they've been looking at several measures: provenance, responsibility, Shapley value. It turns out, you know, they use the same results here because this is a simple query. Yeah. So I'll be talking about this in a second. So then, what I first want to, you know, discuss is whether it is related to the workshop. And well, first the organizer said that I can talk about it, so it is related by that account. But you know, a lot of the talks, and actually in the description of the seminar, there's a lot about annotation of databases and annotation by semi-rings. In a sense, this is kind of a, we can view this problem as going in the opposite flow. In annotated databases, the challenge or the problem is, or the question is, how do we annotate the output tuples based on the annotation of the input tuple? In contribution, it goes the other way around. How do we annotate the input tuples by numbers, by these contribution scores, according to their impact on the output tuples? Now, you can also look at it in a different perspective and say, okay, let's look at the abstraction where everything is, every possible tuple is out there, and it may have an annotation, which can be 0. And then the question becomes, how does each annotation of the input contribute to the annotation of the output? Okay, so this abstraction is useful if you want to talk about aggregate queries or contribution of non-tuples. So I'm not going to develop that. Okay, I just make the I put the connection or a possible connection on the table. Keep that in mind, and I'm just going to talk about the contribution. Okay, so contribution of the tuples. There are two principal general ways, domain-independent ways of attributing contribution to tuples that have been studied. One comes from causality theory, and one from game theory, or one family of causality and one family of cooperative games. And in the case of causality, the idea is that we view the source tuples as the reason, as causing the output tuples. And then we use ideas of level of responsibility. To what extent is each source tuple responsible to each output tuple? And then there are several works. Suchi is the commonality of all of them, that adopted several techniques, several ideas, like minimal contingency to get counterfactual dependence on the tuple. I won't get into these definitions because related to this talk. There was the notion of causal effect. The first came from work of Shapley and Halper, and the second from Pearl's degree of responsibility. Okay. In the view of game theory of cooperative games, we view the tuples as playing a game. They play a cooperative game where different coalitions, subsets, can gain their own utility. And then the question is, if all of these tuples play the game, or they collaborate in order to get the utility of, say, producing the correct answers, then how do we share the profit? How do we share the joint utility? Okay, so this is a different way of phrasing the contribution. And then the Shapley value that Daniel mentioned, and I'm going to talk about in the rest of the talk, is one of the main ideas, or one of the concepts of sharing the profit. Another one is the bands of power index that was also studied very recently, and turns out to be the same as the causal effect that comes from causality. Okay, so Daniel mentioned the Shapley value. He mentioned the theoretical justification using the axioms that I'm also I'm not going to I'll mention them again, explain them again. And it is applied in many areas, including in machine learning, Daniel mentioned, and databases. I do want to give a quick explanation because the details kind of matter to the rest of the talk. So what is the definition? A cooperative game is simply a function from subsets of the players. Okay, so we have a set of players, and we have a function that maps every subset to a number. And the question is how to share the wealth among the players. And there is this function that I explain immediately. But what you can see is that it has an exponential summation, which makes it computationally interesting. Okay, so what is this value? Think of this experiment. You start with the players. We want to measure the contribution of the red player, the leftmost player. So we start building a team, okay? We take one player, it has a score. We take another player, another score. Another player. It's monotonically increasing, but it's not necessarily the case. Okay, we go on until at some point, a random point, we choose our player. At that point, this player makes a difference. The impact of this player is the change from 12 to 17. So the delta is 5, and the Shapley value is simply the expected delta, the expected change. Okay, that's all it is. And then what we and others did were basically the usual application of the Shapley value. In order to apply it to a specific setting, you need to choose your players, and you need to choose your wealth function. So in my work with Esther and the others and Daniel, the players are the database tuples, and the wealth function is the result of the query. If it's a Boolean query, then it can be 0 or 1. We also looked at aggregate queries. The question arose, and you can see it in the original publication, but I can say more in the end about how we achieve that. But the utility can be the result of the numerical query. Okay, say sum. What else? We also looked at the contribution of tuples to inconsistency. To what extent is a specific tuple causing us a headache with respect to the violation of integrity constraints? Okay, so for that, the utility was an inconsistency measure. And we looked at several different inconsistency measures, ways of quantifying to what extent is our database violating the integrity constraints. And then Daniel mentioned the T-Rex system. And I'll be slightly more detailed than Daniel, but they wanted, for example, to understand why a cleaning system chose to change some specific value. So they say, okay, let the players be the constraints and the cells of the database, and let the wealth be, the answer to the question, is the cell change? To what extent is the cell changing? And then, they found the contribution of the different constraints and the cells. And we also looked at graph databases where the players were sometimes the edges and the vertices, and the query was a graph query like a regular path query, and so on. Okay, so this is the game. I'll just say that in many of these instantiations, we adopt, what Sushi and others did in their concepts of causality, where we distinguish between the exogenous tuple and the endogenous tuples. The players are the endogenous tuples, and we assume that there are some exogenous tuples that are not part of the game. They are given for granted, and they never disappear. They're never a contingency. Okay, so this is one thing. Okay, so then I said that the computation is interesting, the complexity is interesting, and several techniques that were used. So one is, just translating the formula into some closed form formula and solve it. For example, using a linearity of expectation, because Shapley value is an expectation. Okay, so for example, if we look at inconsistency measurement, and we measure inconsistency by the number of violations, or the number of tuples that participate in the violations, then this is the case. What else? Reduction to queries over probabilistic databases. Okay, so probabilistic databases are not always easy, but when they are easy, we can use them. So I'll say more about this result next. And Daniel talked about knowledge compilation to DNNFs, and their book is also talked about it this week. And of course, if you use an expectation or probability, you can also do sampling. There are some interesting things going on there where you immediately get an additive approximation, but you can show that it is also a multiplicative approximation, and so on. So let me expand a little about the connection to probabilistic databases. And by a probabilistic database, I mean tuple-independent database. Well, if you do not know the concept, then it's important just for 2 slides, then bear with me. But the idea is that every tuple has a number, which is a probability that the tuple actually exists, and all the tuples are independent. Query evaluation means calculating the probability that the query is true in the database. Okay, so there's an interesting connection between, or tight connection between Shapley value and probabilistic databases in one direction. For every Boolean query, Shapley of Q is polynomial time reducible to the evaluation of the Q over tuple-independent databases. And the proof idea is this is a structure that we see frequently in Shapley values and probabilistic databases. First, we reduce the Shapley value to the problem of counting the number of sets of size k that satisfy the query. That Daniel mentioned that. Okay. Then we take our database and we produce from it several tuple-independent databases. Each time we use a different same probability for all the tuples. What we get is that each database gives us a linear combination over these counts of the size k sets that satisfy the query. And all of these are linearly independent. This is a Van der Monde matrix. And we solve that the equations, and we get the counts. Okay, and this is a similar approach to what Van der Broek and the others did for the SHAP score. I'll mention it next, or I'll use it next. And it also arises in the analysis of probabilistic databases. Suchu and Dalby used it in the proof of the big dichotomy theorem. And I used it with Antoine to prove some complexity results about special probabilistic databases. Okay, what about the other direction? This is open. Well, we do not know whether Shapley of Q and probabilistic query evaluation over Q have actually the same complexity, or they are polynomial time in the same for the same queries. We do know that this is true for conjunctive queries without self-joins. For both the tractable cases or the hierarchical conjunctive queries. Okay, so that was the first part about the contribution of tuples, and now I'll use the rest of my time to discuss some recent work, still unpublished, with my collaborators, Peter Lindler, Christoph Stanke, and their PhD advisor, Martin Goy. And here we wanted to use this concept of a cooperative game, Shapley value, in order to measure the importance of query parameters. Okay, let's look again at the query that we started with the high salary, low salary. But now I spell out what exactly I mean by high salary, low salary. I say low is smaller than 40, high is higher than 90, whatever currency you want. And so we can ask, how arbitrary are these parameters? Or how critical are they for the query? Remember, I wanted to see whether there are cases, or to what extent there are cases of low manages high. So, if I slightly reduce A to 40 to 35, then I miss that I get several of these instantiations disappearing. If I change B slightly, to 95, then most of the cases disappear. If I play with both of them, then suddenly there are no cases of this query. Okay, so the query is false. This is also a question that you can ask, not necessarily about inequalities, but also about the constants of a conjunctive query. Here we have a very simple atomic conjunctive query, R173X. I'll explain what's interesting about this query. The database, I use a factorized representation. So basically, I do not give all the combinations, but rather use a product for concise representation, relational algebra. Okay, so what's in the database? This is one relation. Every tuple has either 1 or 7 in the attributes A and B respectively, and C can be anything and D can be anything. The result is A to G. All right.
Benny, you have about 3 minutes left. Okay.
Okay, I'll be quick. I'll mainly explain the problem. Anyway, the importance of this example, what's interesting in this example, is that whatever change you make to your parameters, it won't change the query. Okay, we have here 3 parameters, but we can see that 1 and 7, are quite particular, whereas 3 is really arbitrary. But again, changing each one of them doesn't change the output. And yet, while P3, behaves totally symmetrically to the other possibilities, if we change P1 and P2 at the same time, then suddenly the answer becomes empty. Okay, so we want to be able to quantify the contribution or the importance of these parameter values. And there are several ideas that were discussed before, and maybe Britt will talk about cherry-picked queries. And again, we wanted to talk about to see the implication of or the application of the Shapley value. And as Daniel mentioned, there is this issue that you cannot just throw away parameters, okay, like we do in other settings, because without these parameters, the query is not well defined. So what do we do? And this situation is what you see, what Daniel explained with features in machine learning, where they use the SHAP score. What is the idea? So here we have an input, and these are the feature values, and these are our players. And now, given a coalition, we say this is the game. Use these features. For the others, throw them away, but replace them randomly. And your utility is the expectation of this value. This is the idea behind the SHAP score. Then you use Shapley, the Shapley value for this specific cooperative game. And we do the same. I'll just say it quickly. We do the same with parameters. Okay, we now have a query with parameters, QP, and a database, and it gives us a result. And given a coalition, we use these parameters. We replace randomly the others. Well, unlike the case of a classification or regression, now the random result is a set of answers, and different changes can cause a different change of the result, okay, in the set of tuples. So we use the similarity between the random result and the actual result in order to evaluate the utility of the coalition, okay? And we looked at several specific similarity measures and studied the complexity of them and so on. Okay, and you can also look at this problem from a different perspective. Say, okay, why do you look at fixing the coalition? What we are interested in, for some it's more intuitive. What we're interested in is what happens when you change the parameters of the coalition. How does that affect the query? Okay, so you can also switch the game and say, okay, replace the values of the coalition, then use the other values. And then the question is, or the utility, a group has a high utility if its change with respect to the actual result is high. So here you use a dissimilarity, okay, which we use as K minus similarity. And the interesting thing is that these give the same Shapley value. These are different cooperative games, but you can show it's not very hard that actually both of them give you the same Shapley value, the same SHAP score. Okay, so I won't go over the results. They are listed here, and well, I can show the writing privately with whoever asks. And I'll just now conclude. So we talked about contribution measurement in databases. This is not new, and we've seen past results based on causality. And we've been looking at the application of cooperative game theory. And I talked about several deployments, database queries, database cleaning, query design. There are tight connections to probabilistic databases, and there are some interesting open problems there, and there are many interesting directions for future work. And specifically for this seminar, I would stress, better understanding the connection between semi-ring annotations and contribution annotation. Okay, and that again has impact on non-monotonic queries, aggregate queries, and so on. That's all. Thank you.
One Fokia, yes.
Hi, Benny. Thank you very much for this nice talk. Do you have any example of a query with self-joins, which is hard for probabilistic evaluation, but it's easy for Shapley?
No, actually, we don't. We don't know. This is the open problem. It may be the case. We conjecture that the two have the same complexity.
Okay. So,
but we don't have a proof for it, except for the case of cities without self-joins. Yes.
yeah.
No, it's a very good question. This is the key of the question. Yes.
And a little joke. Your example was very realistic. I spent 4 years full-time at IBM Almaden, and I was managing Ron Fagin. So
I see. Maybe I knew that. Maybe that's what I have in mind unconsciously, because I worked with both of you.
that's
that was it.
Okay, so we will continue with more questions at 12 for some time, but let's thank Benny again, and Brit, you can connect.